All right, so we're going to try to write a recursively defined function for this sequence, 6, 10, 14, 18, and 22. Now you can see above there, I've also got our term number for each term, just so that we make it really clear which term number we're talking about at any time. So the term number, we're going to use the letter n to refer to that. And then the value of that term is going to be output when you input that term number. So for example, when I wanted to say the first term, I could describe it as f of 1, that would be the first term, and then I would say what that term equals. It's 6. And that's actually the first line that you need to write when you go to write a recursively defined function. Because anytime you write a recursively defined function, you need 2 lines. The first one tells other people where the sequence starts. So the first number in this sequence is a 6. Now the second line that you need tells them where to go from there. So as I look at this sequence, it's pretty clear that every step that I go through adds 4. 6 plus 4 makes 10, 10 plus 4 makes 14, 14 plus 4 makes 18, and so on. So in order to create this second line, I want to say not just how to get the second term, but I want to say how to get any future term. So instead of using f of 2, we use f of n. That way we're saying that that term number can change as we go. This is always our way of referring to the next term. Whenever we see f of n, that's our way of saying the next term, and then we always say, how do we get it? Well, in order to find that next term, we always have to do something to the previous term. And if f of n is our way of saying the next term, we use f of n minus 1 to say the previous term. Because if I'm looking for term 2, I have to use term number 1 to find it. If I wanted to find this 10, I had to add 4 onto the 6. Or if I wanted to find term 3, I would have to use 1 less, term 2, to find it. Term 3 is term 2 plus 4. So this f of n minus 1 is our way of saying the previous term. And then we have to tell people what to do to that previous term, which in this pattern was a pretty simple add 4. It's an arithmetic sequence that added 4 every step. So that's the second line. Now there is one more part to that second line, and that's a rule that tells us when we can use that second line. It's called our domain. The domain basically means the inputs, which n is our input here, that make sense in the problem. So in this problem, we already know when the input was 1, the output was 6. So we don't need to use that for the second line. What we need the second line for is for all the inputs higher than term 1. Because if I want to find term 2, I have to use term 1. If I have to find term 3, I have to use term 2. So every step that I'm using this rule of take the previous term and add 4, I'm starting that from step number 2. So I say at the end of this, some people just put a comma there, some people put like the word when, but n, the term numbers, are greater than 2. Now if we had started from a different term number, like for example, if this had started from term 0 was 6, then we would have n is greater than or equal to 1.